should look into that also. And the last part will be on RCC building, the more or less engineered type of building. So in the seismology, the first of all, what is seismology? That is a study that actually let us know the generation of the earthquake, generation of any kind of a wave, propagation of it, the recording, the analysis of the wave, and the sources of those waves in the earth. Okay, it may not be always earthquake, it may be some other type of propagation of the wave or some kind of activities which may not lead to an earthquake, but maybe lead to some other kind of the volcano or those kind of things also come under the seismology. Now, if you see the interior of the earth, it has three distinguished parts. It's a sphere. It has a crust, which is where we actually live in. So there are two types of crust. One is called the continental crust and one is the oceanic crust. So below the ocean and below the land, and the surface of the land. That is the surface, practically. It is a solid matter. Then there is a mantle, which is a viscoelastic thing and very hot. And then below that, there is the inner core, which is bit of solidified things and has a heavy density. So these three layers of the earth create some dynamic action. So how this dynamic action is created? Because the mantle is viscoelastic and hot, there is a pressure and the temperature gradient. What is gradient? Gradient is the change of temperature in a particular distance or so. So if there is a change of temperature or deviation of the temperature, differential pressure and temperature exists in a certain depth, there will be a convection current will be flow. Just like if you just boil a cup of tea or milk or something, the way convection current is created, similar way the convection current is created. The right hand side figure will give you a kind of idea. And because of that convection current, there is a drag force which will be applied to the crust. So they will move in different directions. So based on this, geologists actually found that the earth is actually consists of the 7 major tectonic plates. These plates are the crust and the oceanic and the continental crust, which are not actually uniform and we call continuous. There is a plate boundary. And these plates are moving in different direction and the different geologists, and that creates the problem. Because if it is moving in same direction with the same speed, so there is no such differential changes. And if it is moving in different direction and with a different speed, sometimes it is coming towards each other, sometimes it may slip with each other, sometimes it may go away with each other. So that will create some kind of a strain, something like a spring. If you just push it, it will be actually absorb a little bit of energy that called as a strain energy that was induced in the spring. And after, if it is crosses the limit, it will try to bounce back. So similar things happens over here. The earth mass is itself is a elastic thing. Maybe it is not elastic that way, it is not that much elastic like rubber or maybe the steel or maybe anything, but it is having some kind of elastic property. And in geological timeline, it will be actually pushing, or there can be a different type of formation of the geological the features. At an average, it will actually move by tens of centimeters per year, something like that, maybe 20 centimeter, 15 centimeter, something like that per year. And that creates a strain energy, and that strain energy will going to release after some time, and that involve some kind of seismic wave. Okay, so that strain energy has to actually, when it is actually crosses the boundary of the limit of the particular storage limit, it will going to slip with each other, and there is a kind of a vibration, and this vibration generates the waves. Now, there are two type of waves. If you just examine the waves that generated by the sleep, one is called body wave and one is called surface wave. You understand what is that? Because the sleep will be generated below the earth, right? So from the earth, below the earth, I mean the point where actually the sleep is generated, below the earth in the sense below the surface of the earth. Initially these two waves will be initiated, P wave and the S wave. You see in the right hand side the figure is given. The P wave is called the primary wave, which is little faster than the S wave from the speed point of view, and S wave is called the secondary wave, or sometimes it is also called the shear wave. So you know the way it is, one is a longitudinal kind of a wave and one is a transverse kind of a wave. When this two wave reaches the boundary or the surface of the earth, it creates two very complicated waves, love wave and the Rayleigh wave. Those waves are not that simple. That waves are actually having a elliptical motion or something, sideways, horizontal plate motion or something like that. And these two are very, very dangerous. These two actually depend upon the lot of property of the earth and the earth mass and all. So, and that will actually lead to a damage or whatever. So, from this point of view, let us see some of the basic definitions. So, there is a fault. What is a fault? The fault is those boundaries. So, one part of the fault is maybe Eurasian plate. The other part is maybe the American plate or maybe the Australian plate. So, those are the fault lines. So there is a strain energy generated in that. So somewhere after maybe 40, 50 years or somewhere, the sleep is occur, and that particular point where the sleep is occur is called the focus center or hypocenter of the earthquake. This is not the epicenter, right? This is not the epicenter. Now, if you just draw a perpendicular line to the surface of the earth, that particular point is called the epicenter. We may say that the earthquake occurred in the Nepal and the epicenter is 200 kilometers northwest of Kathmandu. So that doesn't mean that there is a kind of, in that 200 kilometers northwest, in some village there is a sleep. No, the village is exactly above the hypocenter where the sleep has been occurred. And now this depth is called the focal depth. Now, you understand, if the depth is shallow, it is the magnitude of the earthquake is very high, or the impact of the earthquake is very high. And if the depth is larger, then it will be a less impact. And now, from this, suppose that is a village, that epicenter, from that epicenter to a nearest town or nearest habitat area is called the epicentral distance. The radial distance or the straight line distance is called the epicentral distance. So if I want to say the Kathmandu is the city which is very near to the epicenter, I may say it is 200 kilometers away from the epicenter. So you can imagine that, okay, it's 200 kilometers away. So if I say it is only 75 kilometers away, you may feel that yes, the devastation will be much more, something like that. So from this point of view, if you see the seismic map, every country has its own seismic map, and they actually collect the data. There are recording available each and every day. There is a small earthquake is occurring in those plate boundaries, which sometimes we may not feel, but instrument can feel that one. We record that one, and every maybe after 20 years or 15 years, we revised this seismic zone. So presently, India has 4 seismic zones. Sorry. Zone 2 to zone 5. Before the Bhuj, it was 5 zones. There was zone 1 also. But after the Bhuj earthquake, it was revised, and zone 1 and zone 2 are merged together. So now you see the red and the orange one is the zone 4 and zone 5, which is very, very sensitive zone. And you see this almost cover our maybe 30%, around 30% of our country. And in that, if you see, Delhi is there, Chandigarh is there, maybe very near to Lucknow is also there, Patna is there, Assam, whole northeast, Dispur and the Guwahati, every cities are there. In the west, it is Bhuj is there. Even if you see the Delhi, then there's total NCR, the Faridabad, Gurgaon, every cities are in that particular zone 4. And a whole Andaman and Nicobar Island are in the zone 4. Interestingly, the southern part of the Bengal, the Sundarban area is also under zone 4. If you see that tip, that one. That was because of there is a fault line existing in between the Meghalaya and those Sundarban area through Bangladesh. And another fault line is there from Bangladesh to somewhere just central part of the Bengal. That is, they called as a hinge. Some hinge is there. So because of that, this probability of the earthquake in those areas is quite high. And also it is radially very near to the Andaman. So now from this point of view, we have some goal. The government of India has some goal. I mean, each and every the country has their goal for the earthquake resistance design. See, that depend upon our economic strata and our total population. Those, you have to actually very practically look into that. The goal which Japan or maybe the USA has adopted, we cannot just directly follow that one. We have our own problems, right? So we are not actually focusing to earthquake-proof building. We are focusing to earthquake-resistant building. You have to see what is the slight difference between this proof and resistant. Proof building means whatever may be the earthquake, impact, Richter scale, nothing will be happened to my building. So something like that was the goal of maybe the west coast of USA or maybe the whole Japan. There was much more, those lands are much more earthquake sensitive with respect to our country. And they are more the economically stable country. But we are actually thinking of the resistant building. What is the resistant building? So clear cut, there are 3 primary type of the banner we have put in our goal. The first one is infrequent minor earthquake. See, the earthquake is also something like, if the earthquake, the intensity of the earthquake, I'm sorry, not the intensity, the magnitude of the earthquake is measured by the Richter scale. So the Richter scale is, suppose 5 Richter scale is equivalent to some energy release. You can actually calculate by mathematical formula, and that can be how much joule energy you can calculate. So if the earthquake is 6 Richter scale, just 1 Richter scale above, as it is logarithmic, the magnitude of the earthquake, if increased by 1, the release of energy is increased by 31 times because it is logarithmic in scale. Okay. So, and something like 1 Richter scale is equivalent to 31 times. So, if the Richter scale is smaller, maybe it is 2 Richter scale, 3 Richter scale earthquake, it is very frequent. Maybe in the Himalayan zone, maybe per day 2 to 3 times earthquake is occurring, whose magnitude is almost like 2 to 3. You and me cannot felt it. Maybe some animal can felt it, or the instrument can felt it. We can felt maybe after 4.55 onwards, or maybe 4, like we can felt. Right? And the earthquake like 6 onwards, or maybe the 7.5 onwards is devastating kind of thing. And 9 is totally ruinous kind of thing. So the frequent minor earthquake are very frequent. Daily 2 to 3 times you may occur. Maybe a kind, or maybe in case of the earthquake like 5.5, maybe once in 5 years it may occur. The earthquake like 8 Richter scale, it may occur in once in 80 or 100 years, something like that. That is the frequency and the and the magnitude of the relation between them. So in the frequent minor, the earthquake is called serviceability level earthquake. And we should design the building such a way that the service of the building should continue. So suppose after 5 years, there is a 5 Richter scale earthquake. So, okay, our earthquake will stay for 120 seconds, 90 seconds, something like that. But there should not be any problem in the service level. That means there should not be any power failure. There should not be any short circuit. There should not be any damage in your water supply line or the sanitary line. So those are, I mean, you can just after that, there may be a little panic, but after that you can work. Okay, so the earthquake should not cause any kind of that kind of a panic. I mean, panic in the sense you may feel and then you may act accordingly, but it will not be like it is panicky like that you are shouting and you are just trying to escape. So this type of earthquake is expected 10 times during the life of the building. So next one, the second one, we say that in occasional moderate earthquake, suppose it is around 6.57, something like occasional moderate earthquake. See the last line, this type of earthquake is expected once or twice during the life of the building. This earthquake is called the damageability level earthquake. So in this earthquake, we should design the building such a way, we should prepare. So no structural damage should be lead to loss of life. So there is should not be any crack in the column, beam, slab or foundation. Repairable structural damage like falling of concrete cover, etc. permitted. Maybe some crack in the wall is permitted, some kind of the small falling of the clear cover or some portion of the concrete small part is repairable kind of things permitted. Okay. Now what is the last and third one? The rare major earthquake. Rare major 8.5, something like 7.5 onwards. Rare, last line. This type of earthquake is having a very low probability. Maybe once, may not be. And this is called the safety level. So what is this? How should I design? Non-structural and structural damage should not lead to any loss of life. So I'm expecting some damage. Even I am expecting some structural damage also. Okay. So, but that should not lead to collapse of the building like pack of card, and that should not lead any loss. See the third line. The damage may beyond economic repair. That may lead to a partial and total demolition. Fine. After the earthquake is over, I can inspect the building, I can repair, and if it is beyond the economic repair, maybe it is too much, I can demolish the whole building and reconstruct. But there should not be any pack of card damage or something like that. So we have to ensure that one. So this is our India, in our country, as far as our country is concerned, we are going to see in this manner. So let us now go to the part A, where I will going to talk about the earthquake resistance machinery building. And now you should see that the design should be such a way that I will not going to damage the building. The building should not be damaged such a way that I will not get any time to evacuate. So there should be a sufficient time in my hand, even if the earthquake comes in the maybe night, midnight, 2:30, something like that, when everybody is sleeping, I should have sufficient time to escape from my house if there is a rare major kind of earthquake. The building should behave like that. Building should give some time to escape. So in this machinery building, this is the typical 9 or 10 points are there, where we found there are a lot of design defect or maybe some kind of construction defect. See, whenever I say design defect, you should not actually think of there is some problem with your issues like the circulation, or maybe those are we actually feel like the design issues like circulation, the orientation of the rooms and all. No, that is the soft part of the design or some of the innovative part of the design. The design issues are the shape, design issues are the volume, design issues are the placement of the interiors, wall, or those are the design issues. So you see there, this is a lot of problem occur. There may be bond deficiency in the bond in the corner without some kind of a vertical joints or whatever. So that is a problem not involved in the design, but it is definitely a problem of the inspection or maybe construction problem. The material problem, poor quality of the adobe or maybe the bricks, and without having some kind of the proper mix or sorry, the proper mortar you may use. So there are maybe some kind of a long wall have some kind of a lack of horizontal reinforcement things also. There are large openings, that may be a design issue. There are many openings, many high walls and all high openings like door, and next to door there is a window. So there are there is not so much of bonding between the roof and the wall. There may be a very heavy tile or some roof is there. So something like that. So from that point of view, if you see this particular 10 problems, we can have lot of precautionary measures, like we can actually implement some kind of box action. I'll come to that one after another. We can actually provide some kind of a seismic band. We can think of strengthening the openings. We can actually ensure the stone machinery and the bonding, and we can provide sometimes a confined machinery. So those are the things we can actually, if we just ensure this 5 and maybe 1 or 2 more something, then your machinery building will be safe. Safe in the sense it will give you time to escape. So the box action, there are walls, and there are 4 walls. Suppose you take just one single small shell or room. It has 4 walls. 2 are in the one direction, and 2 are on B are in the orthogonally opposite direction. They are tied together. But when the earthquake comes, earthquake is inertia force. When it comes in one direction. Maybe it is perpendicular to A, or maybe it is perpendicular to B, or maybe it may not be perpendicular, maybe in one direction. So suppose if it is perpendicular to A, perpendicular to B, suppose as per this particular figure, A is very strong with respect to the direction of the force. Why? The depth of the wall A is higher with respect to the direction of the earthquake shaking. So A will be tremendously behave properly to fight against the earthquake. Okay, so something like this, maybe you can say the depth will be actually going to create. Stop this particular presentation now for a minute, and I will sorry, I will show one small demonstration. Suppose I have a, can you see this scale, the steel scale in my
Yes,
hand?
sir.
Okay.
Yes, sir.
Suppose, see, suppose if I try to bend this scale like this, when you see the thickness as a depth, as of now, the elevation, you are seeing the depth as the thickness. It is maybe 1 millimeter or so. It is very easy to bend. Very easy with my 2 finger and this thing. Right? If I just orient this particular scale like this, now in the elevation you will see the depth is the width, which may be 1.5 centimeter or so. It's very difficult to bend. Very difficult. You cannot bend it. It is a steel scale. You cannot bend it, but you can bend. Why? Because the force I'm going to apply, or the moment I'm going to apply, is actually encountered the larger depth. But in the same, otherwise, in this case, if my moment or maybe the force I'm applying is in a smaller or very tiny depth, so it is very easy. So depth will actually kind of the play. And actually, it is not the depth, it is the moment of inertia will going to play. So that is why, again, I'll go with this PPT. So now you see the A, if the direction is the parallel to A is fantastic. A can resist, but B will not, because you see the depth of the B, resisting depth is now only the thickness of the B, not the length, right? So there is a problem. But if there is a good connectivity between A and B, You see in the corners, if there is a good connectivity, they will act as a box action. So some load can be transferred from B to A, and the actual loading on the B will be little less compared to if there is no box action. So you have to practically ensure there is a wonderful action is created by this box of A and B, the walls. So please remember, when I'll go to the last one in this particular machinery, the confined machinery, it will actually going to ensure that this kind of a box action. Otherwise, you can think of something like what we do in the brick wall kind of a connection, 90-degree connection, is the teaching, right? So like that, we can actually making the bond. You may encounter some kind of a shelves, or maybe some kind of the enlarging that portion by kind of a brick pier or kind of things to ensure the box action. That is number one. You see the damage due to the corner damage because it is not playing properly. You have to make it little bit play such a way that all four walls should act as a very good friend. Okay, and they can share the load by each and all. So something like the concrete, the fundamental of the RCC. What happened when I give the tensile zone the steel? The tensile stress is taken care of by the steel because they know each other. They know each other by good bonding between them. If there is a very good bonding between them, they know each other. Steel know that this concrete cannot take tension, so I have to take the tension. And concrete knows that above the neutral axis I have to take the compression. So the fundamental thing is that there should be a very good bonding between the steel and concrete, and that is why the steel is there is the twisted steel and all these things are there to ensure the bonding is better between the steel and concrete. But suppose if there is the steel is actually not having that kind of a bonding. Steel is in a suppose there is a small duct like things, and you put the steel and you try to put it in under the load, it will going to crack because there are no bonding. Okay, just imagine there is a slip between the steel and concrete because there is no bonding. There is a lubricant between the steel and the concrete. There will be no transfer. So if there is a bonding between these two materials, they will know each other and they will act as a very good friend, and then there will be a transfer of the load. Weak will give the load to the strong, and strong will very happily take the load. Provision of the seismic band, the number 2. These bands are most important things. These bands has to be given in the various layer. What is a band? It's a RCC beam like thing. So even if it is a machinery building, doesn't have the column and beam, this band has to be given in the perimeter wall. And this band has been located in the various level. The one in the plinth, one in the lintel, one in the roof. And if it is a gable roof, there can be a gable, triangular kind of things also, with the band also. But at least in these 3 levels, band must be there. And out of these 2, the last line if you see, the lintel band is most important of all, because somehow we give the plinth band or the plinth beam somehow. I mean, or maybe that is under a kind of a ground and there is a enlargement of the foundations and all. They can take care of that. It is also having some kind of a roof structure which is RCC that can also take care of some kind of the unification. But if you go with a split lintel, you see sometimes we just curtail our cost and we give the lintel something like this. That is called only over the openings. And suppose there is a window. So again, I will give a like this, which is a discontinuous kind of a lintel. So we will save some amount of money. If you calculate, it may be around 3% of the total cost of the building, but it will actually lead to a unhealthy on the birth of the building, unhealthy child, like in the very beginning of the building. It will actually create a lot of other problem, like if there is a uneven settlement in the foundations and all. Plinth will first protect, and then secondary protection will be given by the continuous lintel band. So lintel band is must. Roof band is also must. I mean, there must be a kind of a small band. So this band will actually act as a rubber band. So you're providing some kind of a rubber band to various levels. Okay. You know, some people have some problem in the shoulder. Some people have some problem in maybe in the waist or somewhere in the back side, maybe slip disc or so. So doctor prescribes some kind of a, that belt. Okay, maybe some arthritis and all. So those belts are something like this seismic band. You are providing some kind of a belt in your chest or maybe in below chest or whatever. And then it will be actually from some kind of the damage or something like that. So it is kind of a belting, some kind of a garter band, rubber band you are actually tying up all the things. And it will act as a unified manner. So in earthquake, as it is a inertia force. So if you are actually design a building, and by virtue of the construction method, such a way that things will be practically going to have act as a unified way, it will be always going to be better. Now, in the sense, if you see this Latur earthquake photograph, the first photograph in the left hand side is collapse of the building because of that building was having no lintel band, or maybe a split lintel band or something like an arch kind of thing. There is no continuity. But in the second photograph, the same area, the Latur area, it also experienced the same level of earthquake. The construction of the building is not that good. You see, it's a normal kind of thing, but it has a continuous lintel band which actually saved the building a lot. You can just compare. So now you may say that it will going to give you a cost. Yeah, costs, but see that what are the section details also. So below you see you may actually go with a 75 mm small RCC with 2 reinforced hook. Enough. If you think of going little larger, 150 is 6 inch, which generally we go for a lintel beam depth with accommodating chajja and all. Okay, 75 is bare minimum. You can just keep. You can actually continue the 75 mm, that is 3 inch depth of the lintel band throughout your building. And whenever there is a chajja is required in just opening area, you can go enlarge it by 150. That can be also possible. In village area, yes, people are actually struggling to actually investing money. So if they say that you have to go for a reinforcement 4 bar or 2 bar like that, there may be a little bit of hike in the cost. Even our code and other the bodies are actually allow the wooden bands also, because in the village area wood is cheap. Maybe you can go for seasoned wood, and instead of the reinforcement bar you can go for the wooden band also. In fact, you can sometimes use the bamboo also, bamboo strip also, strip of bamboo. Bamboo is very good in the tensile case of a thing, and it is a kind of a wonderful property in case of a tension. So of course you have to actually season it. You have to actually make it some chemical treatment on the bamboo, and then you can use it. Next, third one, strengthening the opening. Even if you go with the seismic band, horizontal bands, still you have some problem with the opening, because you see the wall. A wall may be a solid wall without having any window or door, or maybe having some puncture or opening by virtue of the window or door. A solid wall is definitely having its own stiffness, and it will participate to protect from the earthquake loading. It will actively participate. The wall with punctures also will try to participate, but it is weak. Why? Because it has some punctures. Due to the small punctures or whatever, it is weak. And due to this weakness, it actually start propagating some cracks in the initial jerk of the earthquake. As you see now in this particular photograph, by virtue of this lintel band, roof band, and the foundation plinth band, the total building wall and also the openings, the total building wall has three sub-units. One is called spandrel machinery, which is above the lintel level, where may not be any opening. Maybe there are some ventilators, small ventilators, but it is not that major. There are wall piers and the sill machinery. Wall piers are the small pier-like portion of the wall, which is in between the sill and lintel level, and it will be actually in between the two openings. And the sill machinery is the below the sill to the plinth. So these three, you see, it will behave now because of this particular things are punctured and they are bifurcated or maybe divided. They will act in a different manner. And finally, in time of earthquake, it will going to crush, it will going to fall like this. Because now the wall pier has to be connected properly with the sill machinery. There is again wall pier should be actually well connected with the spandrel, because if the wall pier is under damage, the spandrel may fall below. Okay, so this kind of the dynamic action will going to create. Now, how to again? I have to give some opening, because the door and the windows are the basic need of a building. So I cannot say that I will not give any door or window. So if I give the door or window, there is opening. So I have to again look into that, how this can be combined together. The answer is you have to give some kind of the reinforcement. See the photograph, there is and it will create a diagonal crack. The crack will initiated in the corners of the openings, and it will start creating, and then maybe after the earthquake may stay for 90 seconds to 120 to 150 seconds. Initially, first 30 seconds, it will start small crack, micro crack or crack. And then it will followed by the widening of crack within next 25-30 seconds. And in the after that, the last 30 seconds or so, it will start damaging you. Okay, so if you somehow restrict the propagation of the crack, somehow do something, so you will delay the propagation of the crack. So this 30 seconds will take 45-50 seconds. The second zone of the widening of crack will take another maybe 45 seconds. The 45 plus 45, 90 seconds is gone. So within that 90 seconds, you may escape. So our principle is this. So how to do that by a particular thing? So this exact location of the cracks are depend upon so many things. So we should not do the research on that, the how and what. So we should have a kind of a simple philosophy to how to protect that crack. As I understand, due to the shaking, because you see, it is something like if you stand or maybe if you stand in a bus and suddenly the bus is accelerated, or maybe a train is accelerated, you see, you will be unstable. Your head will try to retain in the same position, but your leg will go forward. Something happened in case of the building also, in case of the earthquake. The foundation will try to move forward, but the head or the roof will want to stay. And because of that, there is a kind of the twisting will occur, and the rectangular window will now become parallelogram or something like that, and crack will initiate. So if I do something in and around with some reinforcement also, because if the force in this way, it will be crack will occur in this way, right? So if I do something, some reinforcement, if it is given, why reinforcement? Because why a crack will generate? Because if there is a crack, see, you see the come one after another. If there is a crack, why there is a crack? There is a crack because of there is a stress is developed already. Why there is a stress? There is a strain. What is strain? Change of length by original length. Without strain, stress is not going to develop. Okay. So if there is a stress and strain developed by virtue of some action, and overall, if the system is under stable, under equilibrium condition, so there must be a compressive strain and there must be a tensile strain occur. So there must be a compressive stress and there must be a tensile stress occur. You know, the brick wall or the brick machinery is very good in compression. So brick machinery is weak in tension, or those brittle materials are in weak in tension. So if you just provide some steel, then what will going to happen? The steel will going to arrest the tensile stress. Actually, because of the development of the tensile stress or the tensile strain, the crack will going to generate. So give some steel. So initially, whatever the tensile strain will occur initially, see, it will directly not jump into 100. It will start from 1 to 5, 7, like that. It will increase. So initially, the strain is developing and the steel is arresting that one and steel is absorbing that one as a material property, ductile material property. Your propagation of crack will be slowed down. Okay, and it will get, so I told you that 30 seconds will be elongated by 45 seconds or so. The steel is going to help you. So you have to give some kind of the steel reinforcement. It is very easy to give the horizontal steel reinforcement, because if you just go for a brick work, so you put some kind of a steel and then you can go for the, and those steel are very, I mean, it is on, maybe you can go with 6 tor bar of 6 mm only, it will be fine. Sometimes you can go for some expanded the wire mesh also. Something like that is kind of these things also can be provided. Equal width of the reinforced machinery kind of a thing can be provided. But it is problematic to provide the horizontal the things, horizontal. So in that case, you have to use actually the hollow bricks, or maybe bricks with some kind of the hole. Sometimes it is not possible. If it is not possible for this horizontal reinforcement bar to be inserted, you can go with at least the horizontal, sorry, the vertical bars are not possible. It requires this hollow things and all. If it is not possible, don't bother. Go with the horizontal reinforcement after 1 or 2 alternate layers, and it will going to give you good resistance. I will say another thing here. In this portion, out of this spandrel machinery, wall pier and the seal, this is dangerous. This is dangerous. Okay, this is very, very dangerous. Why? Suppose there is a problem, there is shaking, there is a failure, there is a crack development and all, and now the wall machinery want to fall towards your room, or the seal machinery want to fall towards your inside the room. Mostly those areas are covered with some furniture. Seal machinery will be almost covered with the table, with the cot or something. The wall pier machinery will be sometimes covered with the almirah or something like that, the fridge and all those. So actually that will going to fall in between the gap between your almirah and those things. And also the height of the fall is also less. Even if there is no almirah, nothing, if the wall pier fall to your, it will be injured you. It will, maybe there is some bandage or something maybe. But the spandrel machinery is not protected by any furniture, isn't it? It is above the lintel level. Because of the accessibilities and all, we design all the furniture till the lintel level, all the almirah, everything. So, and it is also in higher level. So if it is fall, It's dangerous. It will kill you. It kill people. So you have to protect this. Again, the protection means you have to delay the failure. So you can do one thing. You can insert. Suppose this is your. I'm drawing the section. This is your spandrel section. You can actually, even if the building is constructed also, you can reinforce that one. You can drill some portion, make a hole, and in that hole you just put one bar and grout it. Okay, so here something like that, maybe 1.5 meter interval. You can grout and insert the hole, or in time of the actual construction, you can just place a this kind of a reinforcement, 6.285 reinforcement, grout it. So you, in case of your already constructed wall building, you grout it, place that one, and then the hole, make the hole, put the reinforcement and grout it by 1:4, 1:3 cement mortar. It is giving you excellent the behavior. I mean, very disciplined behavior in the time of fall. I mean, the time of earthquake also. Professor A.S. Arya, he is known to be the father of earthquake engineering in India. He is a professor in the IIT Roorkee. Initially, he was in the Department of Civil Engineering and then probably in the Department of Earthquake Engineering. I am fortunate enough, I met him once, maybe long back, 20 years ago or whatever. So he has some of the videos on this experiment and all, and he has shown, I think it is maybe 5 years back also, I have actually got that. I mean, I've seen that video in YouTube. I don't know whether it is available or not. So one building he has constructed with this, and one without this kind of thing, and this one is behaved really well. It will take so many time, so many minutes to actually start propagating the crack or whatever, and then it will need to fall. So you can actually practice that also, or if you can advise that also in your people when they go for some kind of seek advice for you. Next is ensure the stone machinery bonding. Stone machinery we probably do not use, but if you go to the hilly areas, Uttarakhand and all, maybe of course in the Assam and Bangla, in our Bengal also, if you go to the hilly areas, they used, because it is a local available material. The problem of the stone machinery is that it is thick. It is thick, and there is this, in time of the earthquake, there is a split between the two parts of the wall. It will be a horizontal gap because of this thickness of the wall. You may not have a stone which is equal to the width of the wall, and that will create a kind of a discontinuity, and the split will going to happen. So in a lot of building in the Maharashtra, this is again from the Latur, Maharashtra's and all, when there is a, if you just go to the village area and all those, there are a lot of building locally constructed local material like brick, stones, local available stones. See the thickness, and see the width of the stones, something like this. No stone are equal to the width of the wall, and that create the kind of a cracks. No, there is a continuous crack like that going to happen like that, and it will going to dislodge the whole system. You have to ensure something. You have to ensure some keystone. So it is given. You have to ensure some kind of the distances in the horizontally 1.2 meter and vertically 600. Even if you do not have bond, that is called bond stone. If the stone width of the stone is equal to the width of the wall, even if it is not available, try to use this kind of the bonding where lapping is there. At least there is no horizontal or the vertical continuity. That should be arrested. Okay, so probably if it is not possible like that, one stone like this and one stone like this can be used. Okay, so that will actually arrest this lapping will going to arrest the continuity. The last one in the machinery is provide confined machinery. This confined machinery is again developed by CBRI Roorkee. It was in practice, but it is finally mathematically modeled, and then those things are done by them. It is nothing. It is no new type of machinery is confined. What is confined and all? No, same brake, everything can be used. Same motor, everything. With a different construction sequence system. You have to just change the construction sequence system. I will pictorially show you the construction sequence system and you will appreciate that. Let us go to the next slide. See, plinth beam has been constructed. We are left with this particular columns. It can be done when this building is a RCC building, but mostly it is that 2-story building and some small house we construct with the RCC also, RCC columns also. That 10-inch RCC column and 10-inch by 10-inch RCC column and infill wall. In that case only it is possible, this confined machinery. So after the plinth beam, you leave these long bars, main bars are there, then you put the stirrups or maybe the ties, and then we construct the column and then we fill the wall, right? That is our practice. Don't do that. After that, you construct the wall. You construct the wall and come close to the column and make a toothing and the gap like this in corner and everywhere. So just reverse the construction process. Instead of constructing the columns and then infill, construct the infill first and then column should be casted. Cut the column, then go for the higher level, because one floor column casting requires 2 levels, 2 phases. Now I think you understand why this is called confined machinery. Nothing. This is called confined machinery. Change the sequence of the construction. It will ensure a very good bonding, because it is, you see, the bond between the, if you do the reverse, the way we do, first we do the 10 by 10 inch column. So the surface of the column is very smooth. After you remove the formwork, wooden formwork or steel formwork, is very smooth. And then we put the brickwork. So no teething is there. So there is an interface. If a straight interface, problem starts from there. There is, see, the column is the strongest part. It is not participating well with the wall, isn't it? It is not participating because its interface is very smooth and straightforward. But in this case, somehow the column is actually integrated with the wall, and then the participation will be better. So box action, the first one, can be ensured like this. The box actions and all. So this will give you a wonderful kind of the. I mean, my hometown is Kharagpur. So when I joined IIT Kharagpur, I have a lot of friends and all, and they are also of my age. Some of them are constructing their houses in Kharagpur, some plots. So sometimes they consult me. Sometimes I visited their site also. So I practically told everybody that please go with this type of the method. Then you can sleep well in the night. If that will not going to this whatever I told you with the small things, if you can suggest for any kind of your client, and just tell them you can sleep well in the night without any kind of hesitation, you will get at least 90 seconds to 100 seconds to escape from your house if there is a 8 Richter scale earthquake also. So those are the, as you understand, those are the as in the time of earthquake, it gives you the stability and integrity. It gives you the lateral, the earthquake resistance capacity. It will take part in the load sharing way, and the brittleness of the machinery will be also take care of. Next, let us go. I'm going a little late. I should have completed this portion. So anyway, let us see how much I can cover. Earthquake resistance RCC building. The first of all, just like the concrete, I see a damaged building. It is of course a foreign building. See, there is a lot of damage occur. And if you just inspect the damage, you will find the problem associated with the RCC buildings are structural irregularity, inverted pendulum effect, soft story, lack of interconnection, short column. Those are the various effects that create in the this particular building, the RCC building. So in the structural irregularity, if I say, this is suppose a plan of a building, which is a irregular plan. If this is the plan of a building, you'll see the center of the mass for this kind of a plan will be always will be maybe somewhere here. I mean, it will be maybe it will come out of the building perimeter also because of the it is a CG. It is a CG of the building, center of mass. From the center of mass, the inertia force of the earthquake will going to occur because it is inertia force. Inertia force will take the path of the this center of mass. But the center of resistance will be always inside the building, and center of resistance will come from the location of the RCC members like beam and columns and shear wall and all. So center of resistance will give you the resisting effect. Newton's third law. These two lines, two arrows, green and red arrows are equal and opposite. Newton's third law. Fine, it is giving you protection, but because of the this equal and opposite parallel force it will create because of the distance between the COM and COR, it will invite a couple or a twist. Okay, something like that. Again, you just imagine you are standing in a bus or a train, and you are standing, and if it is a regular, suppose it is a square or a circular or a rectangular, the COM and COR will be same point. If it is symmetrical, then this deviation will not be there. At least the couple will not be there. You may have forces to resist and all, but couple will be not be there. It is something like if you stand in a bus and you are holding a bucket of water in one hand and spreading the one hand like this. So what happened? Your center of mass is somewhere here, I mean, away from your body. And center of resistance is in between your two legs. That is a structural member. And suddenly, suppose the bus is accelerated or maybe it stops suddenly. You will lean front and then also twist, isn't it? Because of this particular twisting couple or so. So that is why high irregularities will invite the higher distance between COM and COR and higher twist will be there. So make it simple. Follow the geometric shape. Even if you follow this kind of a shape, three wings or something like this, it has, as I understand, or you also understand, it has three strong axes. And because of the three strong axes, we'll try to now vibrate in two different ways because two are similar axes. There will be a typical problem will occur in the junction. And this is because of the geometrical asymmetry. And this is because of that there are collapse in the building or in the Bhuj earthquake. This was the plan of a building in Ahmedabad, ABCD. There are 4 blocks. The block D was totally detached and damaged or collapsed because of the asymmetry, and there is very few. I mean, there is a very small link between the D and C, and the integrity of C cannot actually help D because there is a few. I mean, small link. You may say, sir, the A and B is also having the same link, but why A has not fallen? Yeah, there may be a different cause, but at least we should see the failure of the D because of the lack of bonding between C and the irregular shape. The wings of D, 2 wings and the H, it is like a H, will behave differently in time of earthquake. So as far as possible, avoid the asymmetrical kind of a scenario. Go with a symmetrical plan and the balanced way. Next is the inverted pendulum effect. You see, this is a very stable kind of a structure where the mass is heavier mass towards the ground or below. But if you provide the heavier mass M4 at the top, it's very unstable. As you feel like if you are with a heavy mass on your head and then you are moving in a car or something like that or whatever, it's very, very unstable. So it has happened. There are water tank fallen in the Bhuj earthquake because it is heavier mass and concentrated in some area, and that only you see this particular two building. The first one, it was under construction. Nothing happened in the other part. Only the failure occurred in the top mass. Even I know that the water tank was not filled with water, but still that created damage. There may be some other problems also, maybe some structural problems also, but damage initiated by virtue of the heavy mass on the top. Even in some portion, it may have you have a heavy mass in the third floor. That also attract high amount of nodal force because of the seismic action. You have to go for that kind of a protection, or you have to think of distributing the load. So something like that you should avoid. You should not provide a single heavy overhead water tank on the roof. You distribute it in the different zones. Or if you want to put, it should be above the staircase or the lift core, because staircase and the lift core are the spinal cord of your building. It has an enormous strength from the lateral force, earthquake generated lateral force. So it is given by the code. The mass irregularities, if you want to check, any floor mass, the ith floor mass should be within the zone of the 2 times of the I minus 1 or I plus. So something like that it should be. Next is the soft story. This is a killing things. So building always given some kind of openings in the ground floor. Why? Mostly because of to park our vehicle, our apartment buildings and all. So this is sometimes or many times it is seen that it is dangerous and it will actually tremendously affect the health and the building in time of earthquake. Actually, see, the first jerk or first attack will come in the ground. And by virtue of two things, each floor will get some stiffness. I have written down K1, K2, K3 are the stiffness of each floor. This K1, K2, K3 will come from the stiffness of the columns and stiffness of the wall. Both are participating. So if you do not provide any wall in the ground floor, suddenly K1 will be very less compared to K2, K3, K4. And this irregularity will not be welcomed by the earthquake. And this irregularity is in the ground floor where the first jerk will going to come, first hit will going to come. And you are going to have the less stiffness floor over there just to accommodate the parking. And that is why this particular floor is called soft, because it is less in stiffness, because there is no participating wall, stiffness participating wall, and SGF or the ground floor, soft ground floor. So this is the again criteria. You can find out the K values and you can check as per the code. So this ground floor, as I just now told you, is not contributed by the wall, and see this kind of phenomena will be going to happen. The building has not collapsed, but it is damage has been started. You see the inclination of the columns in the soft ground floor. You see the next building, it's almost irreparable collapse. Repair kind of a damage has been occurred. The whole building is over a soft floor, only columns. In the Bhuj earthquake, there are a lot of building has been failed because of that, because that attracts the high amount of seismic load in the ground floor. You see, this is the way it has been created. The damage has been created in the soft ground floor. This, of course, the photograph is after the restoration work is going on in that time. But you see, this is how can a building can stand if in your building 10%, 15% of the column is crashed like this, only this thing, the skeleton is left. How this building is going to serve the purpose? It will be actually fall like pack of curd. So you have to ensure that this, I mean, should I do not provide wall, I mean, parking in those? Yes, I have to have, because that is the basic necessity. So my structure, I will actually involve my structural engineer, and if I increase the required amount of column dimension or the reinforcement, such a way that the stiffness is matched, the amount of stiffness in the open floor is matched with the first floor, the next floor, next two higher floors, then I'll be in the I'll be safe. Or in some strategical locations, I may give some kind of a wall, or maybe a shear wall, a little larger amount of the column only in those area, without affecting your parking and the circulation and the turning radius and all those kind of things. We can involve that way also, and you can think of that way, where the car is actually going to hit perpendicular to that. You can have a shear wall, I mean, kind of a part wall or elongated column. So somehow, by virtue of the changing the column dimension, increasing the column dimension, providing some strategical location, the shear wall and all, you can park same amount of vehicle. You can increase the stiffness of the software. See, lack of interconnection. Sometimes this is a practically you cannot do anything. It is a practically site failure. The site engineers are responsible for this. You will see this kind of problem. This beam is not exactly connected with the column. This beam is eccentric. Sometimes we do like that, some addition alteration, and then the wall or beam is little eccentric. Sometimes like this, terminating beam not in the midspan. Sometimes like this, the shear core, that is the lift core, is not very well connected with the other part, because shear core will give you that kind of the strength. You see the photograph. You see the lift core, the top one, standing perfectly, standing like tall tower. Yes, it is a spinal cord, I told you, but there is no good connectivity with the associated part of the building. That is why they fall. I mean, I told you from the very beginning today, you have to have a very good bonding between all the members and all. Then only they can participate well. You see the photograph below. Again, the front part of the building is gone. The lift core and the surrounded by the staircase is still alive, and the things are gone because there is no good connectivity. This one, the last one, this connectivity should be through maybe a small beam or something like that. Not directly connected to the column. There should be a good connection, or maybe a large column, maybe here you can remove this column and then take the beam away like that. So there should be a very good connectivity. You are providing a spinal cord, but the ribs and all is not connected to the spinal cord. So how a man can stand? This is the very funny things, that the column and beam are not aligned with each other. It is a site failure or something like that. I don't think the sensible architect will draw in his working drawing in such a way that it is not matching. It may have drawn, but finally when it is constructed, there is a lot of error. I think it is the final one, the short column effect. The column is basically long or short based on the failure mode. And the long columns are very much general. Our structural engineers are actually designed by IS code, and they have given an elaborate explanation on the long column. So whenever we do any column design, we follow the long column design. Short columns are not so common. It is stiff. It crashes due to the compression. And there is no such design method is available in our code as such. So engineers are actually going to have the long column design, but the short column comes because of some functional requirement. See, I have provided a mezzanine floor. As and when I provided the mezzanine floor, this long column become one and one short. and there are another floor, there are 3 short columns. But my structural design engineer, he has designed the whole column as a long column. But failure will be under a compression mode. I have made a kind of a ventilator and some exhaust fan because of there is a generator or something like that. And this is a glass and this is the wall. So these are the short column. There is a column over a tank and this is a short column. But I have designed as a long column. Okay, so these sometimes for the functional requirement without our notice and all, sometimes we design some kind of a short column. The water tank failure, it may be because of the short column also, I do not know. But at least it is a heavy mass. So if a column is supported by the wall, at least in both the side, it acts as a long. But if the same column is partially filled with the wall and partially is left out for any ventilation, for any kind of opening, those portion will act as a short. So the shear failure will be predominant over here, and this portion will be the crushing or the crippling failure or the buckling failure will be there. Now let us see what happened. See, Bhuj earthquake. Nothing happened. Only problem with this particular, because it is not prepared to take that much amount of shear. And the failure will occur because of the short column. You have just constructed a wall. So what is the remedy? The remedial point of view, our engineers should actually also check the condition of the short column. If it is act as a short column, it should be also prepared for that, for the short column. So there are the new code, the earthquake code has given some kind of formula for just checking that whether this particular column, yes, you design it as a long, fine, but also can be protect that kind of a crashing under the compression load or not. See, this is the failure, short column failure, Bhuj earthquake. So what happened in the short column cases? Because of the shear, there is a diagonal crack will create. It is bulging out, and because of the bulging out, you see there is a opening up of the stirrups is there, and those small unsupported length is act as a short column also, and this is the process. So you have to increase the density of the ties and stirrups, and there are special stirrups has to be made. You have to calculate the amount of these things and all, so that has to be done. I think that's the end of my lecture. I have just, this is the final last slide. So in the RCC, I just going little faster because of the lack of time. So at the end, I will tell you some 2-3 things as a conclusion. Number one, please remember that the building, not the earthquake that kills. Earthquake only, I mean, in our history, only we saw in our history line, if you just go through, it is actually, I mean, it is world history if you go through. It is due to the building and all. I mean, the collapse of the building or the infrastructure, all the things are, I mean, the things are, the loss of life is due to the collapse of the building, not for the earthquake. Number 2, while design, follow the basic earthquake resistance principle. You have, you can go through the IIT. No, that is the disaster management. So I'll say, Professor Mitra may know that one. There's some earthquake guidelines are available online, freely available guidelines are there. You can actually download that one, read that one. It is available in English, Hindi also. I mean, English and Hindi, or maybe Tamil also nowadays. BMTPC, sorry, yes, BMTPC earthquake tips. Please go through that. Please go through that. Build simple and robust. Build simple and robust. Remember, earthquake is a fault finder. You do some fault today, earthquake will tell you that you have done a fault before 20 years before, because earthquake will come after 20 years. That major earthquake will come after 20 years, and earthquake will tell that yes, 20 years before, Mr. X, architect X, and structural engineer Y, both of you have done this mistake. And finally, better design safe than say sorry. Thank you very much. I think, yeah, it is a aerial photograph of area and then superimposed with a crack, kind of a Photoshop made crack. Yes, 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 yes. Yes, that was a Photoshop made crack, not the earthquake made crack. Nothing is written in the chat box. Okay, fine.
Yes, sir. Good morning, sir. This is Shreya here. I have a question. So, when you were discussing about masonry, so I remember that in Ahmedabad, the old vernacular architecture is poles, and they are earthquake resistant. So when I was studying about that, and it said that there was space between bricks to let it move side by side, so that when the earthquake comes, it moves with it and the building still stands. So could you explain it a bit?
I don't know. I am not know that building. I have not visited also. Can you explain me? I mean, what is the philosophy behind the
Yes,
why?
actually, so you might be aware that since Ahmedabad is earthquake prone, like earthquake did not come here, but the waves come to Ahmedabad.
Yes.
So poles, which are the vernacular architecture of Ahmedabad, they still stand to the date, and they are basically made of made of bricks only. So, according to the research paper, it said that there were various reasons listed for why it is earthquake resistance. Courtyard was also one of them that they, and the shared walls also was there. And one of the reasons was that there are spaces between the bricks so that the bricks can move side by side. So when the earthquake comes, the bricks move side by side along the with that force, and like it settles down when the earthquake goes away. So it has flexibility to move side by side. That's why it does not fall.
See, I should not comment in this part because I have not seen that one, and it's very difficult to understand that how a brick can move side by side with a joint motor and all.
Yes, sir. That
Definitely
was
that is
actually
there.
what confused me also.
Because if it is suppose something like a timber joint, which is a flexible joint, suppose you know what is parquet flooring. Parquet
No, sir.
flooring. It is a wooden flooring. It is having some kind of typical lapping and the bonding. It is used for the any purpose of badminton court or dance floor. When you jump on that floor, there is a something like they are actually resilient kind of thing. So that can be happen to be in the wood. You know what is Dhajji Dhauri type of construction in Kashmir?
Yes, sir.
So that is there. I mean, there are wooden triangulations, and in between there are infill stones. So there is a kind of a movement, so they can adjust each other. So without knowing that sliding action of the brick machinery, I am not able to answer your query. Sorry.
Okay, sir.
Yes, sir, issue this sir. So, sir, whether we should provide the parking above the ground, like whether we should have stilt columns, like stilt floor, or whether we should provide parking in the basement where we can have the retaining walls. So, sir, which will be more
Parking in the basement is better option because at least you will get the advantage of the retaining one. But as such, inside the, I mean, in between also there are infill panels are, I mean, not there. So it is again going to have a kind of a soft floor, soft basement floor. So you can go with the stilt, and you can actually discuss with your structural engineer such a way that you can increase the capacity of the column capacity, which required for the structural design point of view. Even if you just do some earthquake engineering software, the STAT Pro or maybe the ETAPS, if you just go through that, they will increase the capacity of the, if you just tell software that you have to increase by some percentage, it will redesign or design the column such a way that the effectivity of the column is increased by load, lateral load sharing is increased by at least 10 to 10, 20, 25%. That will be going to be enough. And if you again further want to do, you can have to have kind of a shear wall. Okay, so, and you have to plan accordingly, as I told you. So you go for the soft stilt floor, no issue, but take care of that. And the orientation and of course or the length of those extended version of the column and the shear wall should be such a way that it should not actually problematic for your car to move out or the turning radius and all.
Thank you, sir.
Good morning, sir.
Good morning.
So, I wanted to ask about the box action that you were talking about. So, in that case, will it be better if we have corners which are not perpendicular but having more angle than 90 degrees? Like if you have walls in, like if you have rooms more in octagonal shape or hexagonal shape, where you
Yeah,
can have.
yes. Actually, if it is 90 degree, if it is less than 90 degree, it is better. Suppose it is a triangle and the total summation of the angle of the triangle is 180. So perhaps if you take a 60 degree, 60 degree, so it is less. If it is like that, it is better. If it is wide like hexagon or so, again it will try to open it up. That is why finally you have to ensure the action, the connectivity action.
So lesser angle is preferred than.
Lesser angle is preferred, but lesser angle is not preferred for our architectural practice.
Okay, sir.
We actually think of 90 degree or more than 90 degree, right? For any kind of our, maybe it is a auditorium, so it is more than 90 degree because it is a fan shape. So something like that. So it is more than 90 degrees. So action will be again, it will be poor action, poor box action. It will try to open up. Yes, yes, that way it will be better. Yes, yes, yes. Circular building is good, very good. Circular, yeah, it has a lot of the line of defense actually.
But sir, architecturally, the acoustical problems might be there.
Yeah, that is there. Gauravji, good morning.
Good morning, sir.
Good morning, good morning. Yes, acoustical defect, lot of space wastage will be there.
Yes. Customized furniture needs to be put in.
Customized furniture need to be put.
So everything has pros and cons.
Yes, yes, yes.
We have to find a solution for
Yes,
that.
yes, yes. That's true. Mostly, mostly it is construction defect. I mean, construction defect and lack of knowledge. These are the very simple things, but lack of knowledge to our engineers and all. And that is why in 2003, 4, 5, that NPCB, AERM and CERM was conducted by ministries. Professor Mitra, you must have understanding.
Yes.
We are in the part of that game.
আমি সিলিকিতে গিয়ে দিয়ে আসছি টনকটা টিএলএসটা সেটা টিএলএসটা
Yes, chat box. Very difficult to say. Scrap trap bond is good enough of a kind of a dead load and the gravity load assimilation or whatever. My gut feeling is that it will be problematic in case of the earthquake. It may save a lot of money, but in time of earthquake, this is my opinion. I am not going to verify it. I have to verify it with other people, but it lacks sometimes the integrity. I don't know. Rat trap bond test has been done in the Anna University once upon a time, just to check whether it is safe against the normal kind of, compared to the normal brickwork or not. And it has got a good marks and passed that test. But lateral stability, I don't know. I have to then consult with people. But my feeling is that it is not. Just a minute, I have to take a call. Yes, sir. Where from? How far the wooden it is, see, it is definitely the steel reinforcement is better, but the thing is that our goal that in case of the even the strong earthquake also, the building should not be collapsed. So that goal can be achieved by the good type of wooden lintel beams. Wooden in the sense wooden reinforced lintel beam or the bamboo reinforced lintel beam. Now you have to, being an architect or maybe anybody, has to see that from whom you are going to design the building. If your client is having a capacity to purchase and do the good work or whatever, you can go for steel. But if there is some hesitations, they want to go for split lintel because there will be some cost curtailment or so, convince them with this kind of bamboo reinforced or the good wooden stripped reinforced lintel beam, which will definitely behave not at par with the steel, but at least kuch to karega. I mean, something it will do, and it will do good.
Sir, I also had another question regarding bamboo. So we talked about that bamboo is good in tension,
Yes.
in case of tension. But
Yes.
so will it be good enough if we have a bunch of bamboos and create a column out of it, and it works for compression also? Will it work for compression?
See, bamboo studies are going on. The problem with bamboo reinforcement is that one of our Professor Damodar Maiti from IIT Kharagpur Civil Engineering, he is one of the pioneer researcher in this area. He has constructed some model house also, but the problem is people are not convinced. Bamboo is, as a construction, as a reinforcement material embedded in the concrete, is behave good in the compression also. Okay, compression also, but as you told, a bunch of bamboo, if I just provide as a long column or so, it has to be tested. And it can be thought for a vernacular kind of a building also. But for engineering purpose, it is very difficult to say, because the strength of the bamboo differs from species to species. That is another criteria. And because steel, wherever you get, is a very quality product, right? It is a factory made thing, quality product. So bamboo is that is the one of the problem is the bamboo. If you just use it all together, but if you use it as a embedded material, as like a reinforcement, it behaves at par steel. I mean, definitely capacity is less, total carrying capacity is also, but that is enough for a residential building under earthquake scenarios also, in zone 3, zone 2, even zone 4 also for a low-rise building. I will not going to suggest if it is a building like G+5, G+4 to above, G+5 and above, a bamboo reinforcement column and bamboo reinforced foundation and all. No. But if you are thinking of affordable masses and for the large scale housings and all, of kind of a walkable flats apartment G+3, it is possible. But people has a kind of a, still they are not very much confident with the bamboo as a reinforced material. As Professor Damodar Maiki told me that we need to break that one and whatever.
So I totally agree with you, sir. People are experimenting with bamboo for G+1 or G+2 structures, but the confidence thing,
Yes.
which you said, is totally means it's the ice which needs to be broken.
Right. Yes. In commercial mall, so yes, your see that are you Nishant? Are you talking about the that soft thing, that if there is lot of display areas, then it is much more soft? Is it
Yes.
so?
Yes, sir.
See, it is not going to be a soft, because suppose you have 3 floors of building and all are shopping malls, all are having windows. See, it is the, what is the softness? Softness is the relative stiffness of 1 and 2 and 2 and 3. See, suppose you have all floors without wall, then it is not a soft, because each floors are having same stiffness. K1 is equal to K2 is equal to K3, K4. Why it is relative soft? Because the K2, K3, K4 are having wall and K1 is having no wall. So it is soft. With compared to K1 and K2, irregularities, I have told in the beginning, mass and stiffness, it should not be irregular. Drastic change, earthquake doesn't like. So in your shopping mall, if there are windows, so it has pillars almost, and it is a skeleton. Each skeleton, each floor level, they have the same stiffness. And there are outer periphery wall, and in between there are window shopping ke liye do tumhara glass panes are there. Fine. Just check the summation of the stiffness of all the element in each floor K1, summation of these things in K2, whether it is comparable or not.
Okay, sir.
Since stadium demand both column free. Pneumatic structure will be feasible, because it is, see, the earthquake induced, the inertia induced force in the earthquake. What is inertia force? It's depend upon the mass, mg, mass into gravity in case of this way. This is gravity, right? Similarly, in case of the earthquake, it is also the m into g, but it is not g, it is some portion of the g, 0.5 g, 0.3 g, like that. So if you can reduce the mass, you cannot reduce this g business or the shaking, the acceleration business. You can reduce the mass. Definitely the amount of things will be less, the inertia will be less. And the pneumatic structure is the possible. Yes, it is possible, as you told rightly pointed out. It is very, it is the mass is very less, and they definitely it is not going to attract that much amount of force. This is excellent solution. Maybe the pneumatic structure with a column freeze, with a tensile cables and all, can be excellent solution for the stadiums, earthquake resistant stadiums and all. The first problem you have get rid of because of the reducing the mass, overall mass of the building. You can have only the floor mass and the mass of the people, and you can have lot of columns over there also below your seat level, below your the sitting level, but above your sitting level the whole roof structure can be given.
Okay, sir. Thank you, sir.
Yeah, that is the reason, Vaishali. That is one of the reason of that kind of the vernacular structure can be. Vernacular structure, if you see, I mean, one of the most important thing is that they are lightweight in nature and they are very regular in nature. We have also studied some of the Bengal, this area, the mud buildings, vernacular mud buildings with thatch roof. And that was the incremental housing. Incremental housing is if the family size is increasing, so they add up one extra room and all. They have a lot of land probably, and they are adding up 1-2 rooms like that. Incremental housing. And we have seen that one also by virtue of our studies with some students. I did the study nearby area. In case of the incremental things also, they go very symmetric. They go very symmetric in the incremental adding up the things. So in the vernacular, the thick mass will actually going to help them from the thermal barrier. It will act as a thermal barrier. Plus, that will going to help them for the consolidation of the center of the mass and also the lightweight. In the other sense, the roof structure is very light. Maybe the wall structure is little heavy, but roof structure is very high, and the symmetrical additions and symmetrical layout of the building provide a very unique solutions and provide the earthquake resistant solutions. Yeah. Yes, yes. Yes, yes. Okay. Thank you very much. It is a very good interaction. At least I'm very happy that students has come out with a lot of queries and a lot of good queries, quality queries and all. Thank you, Professor Mitra. Thank you, Professor Gaurav Singh ji.
Thank you, sir. Thank you
Okay.
for an enlightening session.
Okay. Thank you. Okay. Okay. Right. Okay. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank
Thank
you,
you.
sir.
Thank you, sir.